Today, we're going to talk about something that's, well, it's genuinely beautiful. It's called the art of smart simulation. And it's all about finding a really elegant answer to a problem that's way more common and way more critical than you might think.
So think about this for a second. How on earth do engineers test a brand new jet wing without ever, actually building it? Or how do meteorologists simulate a massive, complex weather pattern? We're talking about things where the stakes are just incredibly high. You can't just cross your fingers and hope it all works out.
Well, the way they do it is by building a digital twin. And the absolute backbone of that twin, its core structure, is something called a mesh. The best way to picture it is like throwing a digital fishing net over a really complex object. It breaks that object down into tons, sometimes millions of simple little shapes, polygons that a computer can finally wrap its head around.
Okay, so what is a polygonal mesh, really? At its heart, it's just a bunch of simple shapes, like triangles and squares, all stitched together to approximate a surface. It's how you take something smooth and real, like that jet wing, and turn it into something a computer can actually work with. A bunch of points and flat faces. It's literally the language these simulations speak. It's the translation from our world to the digital world.
But right away, you hit this classic problem, this trade-off. You want more accuracy, right? So you need more detail. That means making your little polygons smaller and using way more of them. The catch? The more detail you add, the crazier the computing time gets. We're not talking hours, we could be talking days, weeks, maybe it never even finishes. So the real trick isn't just to add detail. The trick is to be smart about where you put it.
And that brings us to the real heart of the issue we're digging into today, which is pulled from this fantastic paper by researcher Yu Yu. It's what happens when adding that detail goes wrong. Because, and this is the key part, doing it the wrong way can actually be way worse than doing nothing at all.
So the standard smart way to do this is with something called an adaptive loop. It's a pretty straightforward cycle. First, you solve. You just run the simulation. Then the computer estimates where it thinks the answers are probably a bit shaky or inaccurate. It then marks those spots, those specific polygons that are causing trouble. And finally, it goes in to refine them, basically chopping up just those problem areas into smaller pieces. And you just repeat. Solve, estimate, mark, refine. Again and again.
All right, let's make this real. Here's a great example from the paper. This is the mesh we're starting with. The simulation runs, and bingo, the computer flags that polygon up in the top left, number 1, and says, hey, there's a high arrow here. So the system marks it. The plan is simple. Just chop that one up into smaller bits to get a more accurate result right there. Easy peasy, right? Well,
this is where it gets messy. This is the naive way of doing things. If you only refine polygon number 1, take a look at what happens to its neighbor, number 5. See that? By adding new points on the line they share, we've accidentally created these horrible, tiny, distorted little edges. We've basically fixed one problem by creating a whole new one just next to it. Not good.
And I gotta stress, this isn't just about it looking a little weird. These are called degenerate polygons, and with their teeny tiny angles and super short edges, they can totally break the math that the whole simulation is built on. We're talking about huge errors that just spread through the whole calculation like a virus, and suddenly your final answer is, well, it's garbage, completely useless. It's like a silent killer for your simulation.
So how do you solve a messy problem like that? A problem that just keeps creating more problems? Well, it turns out the fix is just incredibly elegant. It all comes down to a simple rule.
The whole solution is built on this one powerful idea. The goal is to make sure that any edge in your mesh has at most one hanging node. Okay, what's a hanging node? Just think about it. When you split a polygon, you add a new point in the middle of its edge. If the polygon next door doesn't get split, that new point is just left hanging there. The rule is just never ever let an edge have more than one of those.
So how does the algorithm actually enforce this rule? It's so smart, it's almost funny. First, you mark the polygon with a high error, just like before. But, and this is the genius part, before you do anything, you check its neighbors. If splitting that first one is going to break the one hanging node rule for its neighbor, you just go ahead and mark the neighbor for refinement too. It sets off this little chain reaction that automatically figures out everyone that needs to be refined to keep the mesh healthy. It's proactive. It stops the problem before it can even start.
All right, enough theory. That's all well and good, but let's see what this actually looks like. This is the algorithm in action, and you're going to see how it turns a clunky, coarse mesh into something pretty much perfect.
And wow, just look at this. This shows you the power of that one simple rule. On the left, that's where we started, that chunky, basic mesh. And on the right,
That's what you get after 30 rounds of this smart algorithm. I mean, look at that. The detail is just packed in there exactly where it needs to be, and nowhere else. So clean, so efficient.
Let's zoom in on that final mesh for a second. Every single one of those little shapes is just perfect. They're well-formed, well-proportioned. The detail is super dense, yeah, but only right around that tricky corner where the simulation needs it. And here's the most important part. Look at what's not there. No tiny, messed-up polygons, no short edges, nothing. This is a high-quality mesh, and that means the math is going to work and the results are going to be solid.
So, okay, a pretty mesh is nice, but why does it matter? Well, this wasn't just for show. This entire process was done to get a really accurate answer to a seriously complex problem, the Poisson equation. And that's a huge deal in physics, in engineering. I mean, it's everywhere.
And here it is, the moment of truth. On the left, you have the exact, perfect, mathematically correct solution. And on the right, that's the answer our simulation came up with using that smart mesh. I mean, come on, they're nearly identical. That is what success looks like. You get a result that actually matches reality, and you did it efficiently, without the whole thing blowing up.
Okay, let's zoom out for a second. What's the big takeaway? To me, this is all about the journey from something that's complicated and easy to break to something that gives you real clarity, real understanding.
And you know, there's a quote from the author Yu that I just love. They said, "The purpose of this implementation is primarily educational." And that really hits home. It's not just about building some fancy tool for a handful of experts. It's about taking these really powerful concepts and making them easy to grasp so that more people can learn from them and, build the next great thing.
And that really brings us to the final thought I want to leave you with. This whole thing, it was never really just about computer meshes, was it? It's a perfect story about how one simple, elegant rule can stop a whole cascade of messy, complicated problems from ever happening. So the question is, where else? Where else in our work, or heck, even in our lives, can we find a single, smart rule like that to cut through the chaos?